So this session we're talking Torque 4.0. The title, What's Different? It's just kind of the best thing I could think of. Of course, it's been a long time coming, getting our Torque 4 out, and today we'll just kind of talk about some of the things that you can expect, some of the things that we've done to get to this point. And this was working yesterday, wasn't it? That's okay. So this is a list, and by no means is it an exhaustive list. We'll find some more things that probably even now as we talk we'll know what it is, but we're going to talk about installation will be a little bit different to you. Oh, yeah, okay. Thanks. I love IT guys. We have a new daemon. This is for client commands, Torque off D. We have a couple of new optional things. We'll be talking about the MOM hierarchy, job radix, CPU sets CPU sets and NUMA. We've added HWLOC to help us with that. Our communications is all TCP now, and then there's just lots of new behavior and a few other things that we'll be talking about. So first of all, let's start with the installation. One of the things that you'll need now is live SSL-dev. Make sure that that's available. Specifically, Torque is looking for live SSL.so and live crypto.so to be available in order to be able to do your configure and to do your make. Another one that I don't have up there that you might want to put up there is pkg-config. Sometimes if things won't work, you might want to install pkg-config. Is another one that seems to come up missing. So we're just learning things as we are going along and going on different versions. CentOS and Red Hat have some quirks. Of course, we develop on Ubuntu, and so when we get over to CentOS, we find things that aren't working and that we don't expect. We do test on CentOS. In fact, that's what our test bed is on. But I think Isaac has found all of the quirks, and he just wants it to work so he can get his job done. And so we run it. Either he fixes them, doesn't tell us, or he's just getting lucky. The server DB file is all XML, and it's no longer an opaque file. There are two parts to it. There's in the server priv directory is the server parameters that is everything, but then there's a queues directory, and that also is all in XML for all of your queues. So if you ever have a problem and your server DB gets corrupt, you can go in and you can repair it. If you really want to, you can bypass QMGR and you can actually just type in directly the whatever options or attributes that you want. You can type that directly into the XML if you need. Just a reminder, 2.4 and before the job arrays are not compatible with 2.5 and later, so 2.4 is job arrays are not compatible with 4.0, so if you're running on 2.4 and you have job arrays, make sure before you upgrade that you drain all of your job arrays before you do it. The jobs will be lost if you don't. We changed our communications, so it's all TCP. RPP, UDP is gone, and that's what the MOMs generally use to talk to each other. The status updates to the server were done over UDP, and that's all TCP now. So we're not backward compatible, so it's an all or nothing upgrade, but only the communications isn't backward compatible. You're not going to have to drain all your job files. So like I say, make sure you drain all of your running jobs, and any jobs that are still queued, they'll upgrade just fine, with the exception, of course, of 2.4 job arrays. We'll just go on. Torque off D. So we moved to, the PBS server is multi-threaded, and we wanted to improve our performance and response. And PBS IFF has always given us problems. It's never been a really high utilization binary. And so it got replaced with a new daemon called Torque off D. And so Torque off D, it runs as root. It's a daemon that needs to be anywhere that you're going to run a client command. Torque off D needs to be present. It's multi-threaded. It's far more reliable. So you won't get the credential timed out, which really isn't what happened. I mean, we get a lot of times with PBS-IFF, you'll get errors saying you couldn't connect for whatever reason, and they're not always true why they didn't connect. They just PBS-IFF just failed for whatever reason. We found that the torque-off D performs very well, and it'll do a high throughput. We've been able to run several simultaneous client commands through it. John Rosenquist is the one who wrote it, and at one point he had it running, I don't know how long he did it, but he had over 116 million requests had gone through it without any failures. So it's a lot better model for submitting jobs. And for those who need to know, it runs on port 15,005. The MOM hierarchy is an optional feature. We created it to kind of reduce traffic. One of the things that we found with Torque in the past is that because the update traffic was UDP, when the system got busy, then the first thing that, or when the network's busy, the first thing that gets dropped are UDP traffic, and often you'd have MOMs would drop out, but the MOMs really were okay, but because the server hadn't been able to communicate with them in the timeout period, it would mark them as down. And so when we were trying to solve this problem, we came up with the MOM hierarchy. It has a very general syntax. The idea is I want to take MOMs who are physically close in the network and group them into a path. And the path is divided into levels. Top level is the level that will talk. Those nodes will be the ones that send updates to the server, and everybody below will send them up the chain. And so instead of having everybody talk to the server, we just have a few nodes that are talking to the server, and then they're physically close, and so the communication stays in one area, and again reducing the amount of traffic on the network.
What happens if the top level MOM dies?
Good segue. We'll get right there. So here's an example, and in the next slide we'll start talking about that. So we have path. The attribute is optional. It's so like row 1, row 2, rack A, so you can keep track of where things go, and then you can have multiple of these, as many as you need. And as far as the communication goes, so.
Okay, I have a question. Can you back up a slide?
Yeah, sure.
Just out of curiosity, is there any reason that you? Oh, row 1, row 2, row 3. I see. You could put all those in one giant level block.
I wouldn't recommend it though, and you'll see why in a minute. So you probably want one in the one. Anyway, here I'll show you. So this is what ends up happening. So taking the example that we just had, so everybody on that top level will communicate, will send all their updates to the server, but everybody on each level below will send all of their updates to the first available host on the level above it. So we see that all of these are sending their, oh, and I left them host 4. I had to change it. Somebody messed my slide up, and I just changed it at the last minute. We'll call this host 1. So these guys are all updating to host 1, but yet all of these guys are updating to PBS server. And of course down here, all of these guys now are going to host 4, which sends all the updates here and sends them on to the server. So let's say that host 1 ends up going down. Well, then all of the ones on the next level, they go, okay, who's the next available in the list? And I'll start sending my updates to that one instead. And then here we go. Let's say that whole row went away. Then everybody in there like, oh, there's nobody above me. Well, we'll just talk to the server. And eventually, if all those go away, so it's just always a fallback. And the eventual, or the ultimate is, if I can't find somebody above me in the hierarchy, I will tell the server myself. And it's self-healing, so when they come back, they'll discover that they've come back, and then they'll begin to communicate back up through the hierarchy. Oops, let me go back. This is just to show that the middle row went away, and so the people on the 3rd level, they're going to communicate to the top level which will then go to the server. So it's intended to be self-healing.
Do you have any guidance on how, like, what size each row should be?
So this is one of the new things that we just don't know yet. And so we're kind of waiting to see what people do, what they find, how useful it ends up being. One of the things so a couple of weeks ago, we were running into a problem in getting updates, and we found a bottleneck in the architecture. As we've been as we've been doing this, we've wanted to make sure we didn't break any functionality in Torque, and so we've, instead of rewriting it from scratch, we've been kind of just taking this old piece out and putting something else in. The analogy I started thinking of was, I can't use wine bottles because once you break the wine bottle, it's gone. So I'm thinking of whiskey barrels, because they have planks in them, and so we're just kind of replacing a plank at a time in the whiskey barrel, and hopefully eventually we get a new whiskey barrel and we can char it up and start fermenting new whiskey. But so as we started taking pieces away, we found a bottleneck, and so there's a select loop. So there's main loop in the code, and in the select loop it's just looking at all the sockets that have been put into that select loop. Well, the listen port is 15,001, and so what we found is that, of course, on that select, only one request will be taken care of at a time. And so when we started doing our 5,000 and 10,000 node clusters, they were taking a long time to come up. And then we realized we were only getting, every time through this loop, we could only get one mom at a time. And so we bypassed all that, and now we just have a listen thread. And we had some other things we had to overcome, because there's connection tables that contain information that we have to have around. But anyway, we finally did get it working, but now it works extremely. The throughput of it has gone up significantly. And so mom hierarchy, we find on 5,000 nodes, isn't necessary. So like I say, this is new stuff. Where mom hierarchy ends up, its usefulness, we're kind of looking forward to seeing what will happen. The one thing for sure, again, the idea was we wanted to reduce the amount of network traffic coming into the server. So instead of having 5,000 nodes all reporting to the server, we wanted to offload that traffic and just have a few. So the guys who are taking care of the network probably be a lot happier that they don't have all the traffic routing to the single point. And again, with UDP, we found that it was very problematic, and that was what spawned the idea. With TCP, again, it's a new behavior. TCP is going to change the way we work, and so we still have to find out. We created another. So the job radix is a job submission option now with QSub, and the idea out of this originally was to speed up job launches. And we had the opportunity a couple of years ago to go down to Los Alamos and try it out, and we found out that it doesn't reduce time, but we also found out that wire up time is not the bottleneck, or is not the bottleneck that Los Alamos was seeing. However, similar to the MOM hierarchy, it offloads network traffic. So instead of everybody communicating to the PBS MOM, they go through a hierarchy instead. And yes?
Good question. How does the MOM scale the amount of communications that can relay?
Say that one more time.
So if people want to use job radix trees, how many connections can one individual PBS MOM relay? So
the values are anywhere from 2 to 9,999, and I just put that hard limit on there. In practice, we find that actually, if you get up above 10, you really don't see any benefit, going with a really high radix. Radixes of any, 2 to 5 actually, work pretty well. A radix of 2. So we've got a binary tree of 1,000,000 jobs. How many levels is that? 20 levels on a binary tree. and you know, so 3 would be less, 4 would be less. So you really don't have to have a large radix to keep the traffic down.
So every radix level is cutting the communication in half to another superior?
Well, depending on what your radix, like this one's a third. So on the MOM, there is a, so this is for parallel jobs. It opens up a daemon called PBS demux. And PBS demux's job is to get all of the standard out and standard error from all the sister nodes. And with the way it currently does, then I have a large job. Every sister in the job is opening up a port on whatever the MOM is listening on, and then they're streaming up all of their output and error to the mother superior, and she aggregates it and then eventually writes it out, and that's what your .o and .e files are.
So Ken, you add the job radix on the submission. Can we actually do a default job radix in the server so users don't have to keep them in it?
Yeah, we don't have that yet. So for now, it would have to be a Q sub filter, but we could easily put a default job radix in there.
Do you want me to put a ticket in for requesting for?
Go ahead.
You can put our name down
as seconding that.
Seconding that. That'd be really nice.
Next down is 30.
Oh wait, we're not at 30. I think it just became a high priority.
Yeah.
Everybody in the room asked for it. So.
Okay, we'll get that on there.
Does radix control the number of parallel paths down or the number of levels down?
So again, whatever radix size you choose, that's how many paths you're going to have. And
in this diagram, you did a 3.
Yeah, we picked 3.
So there are 3 reporting to Mother Superior, and then there's a binary tree below that.
Right. Well, well, this particular, yeah, I'm sorry. It's not binary. Let me help. It ends up being a round robin assignment. So the host exec list comes in, and so in this case, if it's 3, so this had 9 nodes in the request, and so then it's going to just start with the first 3 nodes, and it's going to say, okay, the first guy in the list is going here, the next guy's here, the next guy's here. Now we're going to go and start on the next one, and add one here, one here, one here, and go back and add. So it'll be a radix of 3 all the way down.
So the radix controls how many talk to Mother Superior.
And how many talk to the intermediate MOMs as well. So if I had made this 10 or 12, then you'd see 3. I have host 1 still. Boy, man, marketing didn't proof my slides at all. Anyway, I would have had 3 reporting. Let's see, I guess I got the pointer. If I'd had a larger radix, I would have had 3 pointing to here. But because I ran out of real estate, I left it at 2. And there would be 3 reporting here, 3 reporting here. And if I had more, then it'd be the same thing. So it'd be 3. So at most, any node, any intermediate node, will have 3 subsisters reporting to it.
If this was a radix of 4, where does it add that 4th one?
It would add a 4th one right over here.
Okay.
And so that your top level is going to be equal to what your radix is. And then as you come down the tree, then each node would have, and so you just have your n array tree as you build it out. Yes. You mean, yeah, so they're just saying having a default radix, you mean? Yeah, so right now we just do the round robin. One of the things, after we got it going and started testing, one of the things I realized, especially after we did the MOM hierarchy, is that we don't have anything right now in here for job placement. So MOMs, again, it's just right now the algorithm is just a round robin. So we could have, one MOM from this far end updating a MOM clear on this far end of the network. And so we'll need to come up probably with some new algorithms to try to be intelligent about who goes where instead of just doing this simple round robin. Oh, real estate on the slide.
Oh.
So if you look right here, I have a job radix of 3. I have 9 nodes.
Right.
And again,
Really, there will be 3 on this one and then 3 on the next. The last one will have any?
yeah. Well, again, it's round robin. So I had my 9 nodes. Here's 1. And so then I said, okay, you get a node, you get a node, you get a node. Now I'm going to come back and it says, you get a node, you get a node, and oh, I'm out of nodes.
Oh, I got you.
And so they end up with 2. If the job, if it had been 10, then he would have 2. And if it had been 11, then he would have 3. And so again, it's round robin. Like I say, we're going to have to improve that algorithm. I haven't thought about it. And actually, we always count on you guys. You guys always have the better ideas. So, any more questions?
Can you have an example with a higher rate of concurrency? This is a 9-node example. Do you have an example you could show us with like 100 nodes?
We could create one, but I don't have one on the slide, no. So, and this is really intended for larger jobs. You know, the job radix really doesn't make sense on a 9-node job. Probably doesn't even make sense on a 500-node job because the congestion's not high. But when you're getting up to 2,000 node jobs and things like that, that's where it starts to make more sense. Again, the idea is to reduce the amount of traffic, the congestion on the network. We don't want everybody communicating to a single point in the network. Okay, CPU sets. We are now using HWLOC to help us to choose CPU sets for a job. So currently, CPU sets just do the next index. So when you get the exec host list, you'll see, you'll have host A/0, host A/1, and right now the CPU set goes and looks at that index and says, oh, I got host A/0, okay, I'm going to assign CPU 0 and I'm going to assign CPU 1. And of course on larger chipset, they're not going to be adjacent. There's a good chance they're not going to be adjacent to each other. But with HWLOC, we are going to schedule the next core instead. So your jobs will be physically close. This will also, right now we're not there, but we're going to be, no. Okay, yeah, let me get it straightened up. Also, this will help us with SMT support. So if we have hyper-threading turned on, then that'll, we'll make sure that we're not scheduling the hyper-threads in a way that's not optimal. So here's just an example. So this is index core. So let's say I have a node index 0, 1, 2, and 3. Like I say, just a really rough example. So I have 2 cores, or 2 cores, and you'll see that in this contrived example, now my job is set across the 2 cores instead of all on the same core. But with the HWLOC, it'll say, oh, well, here's all, these guys are all adjacent, and so we'll schedule them all on the same core so that they're all close, physically close to each other. Yesterday we were having a discussion and realized, let's see, Dan Voss, is he here? Oh, there he is, yeah. And we do have a problem of that, oh, well, 0 and 2 are scheduled, but I need 4, and so now I'm on 4, 6, 1, and 3. So, I don't know, there's more work that'll be done on this going forward, to make sure that we get some more optimal job placement and stuff. So this is just another area that we need to improve. But for now, this is definitely an improvement. You know that for the most part, your jobs will be scheduled, or your CPU sets will be taken adjacent as much as possible to each other. There's some new helps in Torque 4. So HWLOC has to be installed in order to be able to compile, and there is a install script under the contrib directory called nwloc_install.sh that will install that for you if you don't already have it done. And on NUMA systems, there is also another script. I think this one was Bernd Callis, I think, wrote this one, and it'll automatically generate your MOM layout file if you're running on an SGI system, or actually it doesn't matter, it doesn't have to be SGI. If you're just running on a NUMA system, they'll create an appropriate MOM layout file for you. So they'll build board notes for you and everything. Yes?
Okay, quick question, with the job placements that Torque does, is that still relevant if you've got Moab running on top of it?
So, like we were just talking about, so yeah, that's really a David question. But the job, so we don't have the topology aware stuff done yet. That's I know that's in the roadmap. I didn't go to the roadmap meeting. I just know that it's coming up.
Yeah.
Yeah, and I'm not sure exactly how they're going to handle that. So, but it will affect the way. I'm sure it will affect it because it has to. Because we're letting Moab do the intelligent placement of the job, and exactly how it's going to be done, I don't know. Okay, communications. So this is going to be a big one. So the behavior of Torque is, so like I say, the functionality of Torque is really not changed. We've added, like I say, for you, for administrators, we've got Torque off D, we've got optional MOM hierarchy. Users will be able to use job radix if they want. But for the most part, the end user is not going to see anything different. So that functionality is the same for them. But the behavior of Torque 4 is going to be different. And as we get it out there and start using it, we're going to find different things. So we're multi-threaded. And so things are going to be different because it's multi-threaded. And then the TCP communication is going to be different. So one of the things we're going to have to get used to is we'll have new error messages. So there are old error messages that are going to disappear. Anything that had to do with UDP is going to be gone. You're never going to see this premature end of file message anymore. It's gone. So hopefully I don't get a new one that's just as annoying with the TCP, but that EOF is gone. And so there'll be, like I say, a new set of error messages. We've tried to keep everything, we open the socket, we send our request, we get our reply, and we close the socket and we're done. The 2.5 and earlier Torque, they try to they do it over UDP, and they have their virtual connections, and they like to leave them open, and that's what ends up generating that premature EOF file as it's cycling through its list. It says, oh, this one's been idle for a while, we're going to close it up. Anyway, it was really hard to follow and really hard to understand. We weren't really quite sure how everything came. We could just see cases, and we didn't know how to stop it. And so moving to TCP gives us, programming-wise, a lot more control. Excuse me. And hopefully, again, it's a lot more reliable. Oh, one of the other things on using TCP, especially when we get into larger jobs, we had a problem last year at the research center in Jülich, Germany, and they were doing a 3,500 node job, and it just couldn't start. And we were having a hard time debugging it, and doggone, I had to go to Germany. It was a lot of fun. But what we found out was just simply, it turned out that the network, again, was just dropping the packets, because I have this 3,500 node job. So that means, oh, and these are all 8-core systems. So 3,500 times 8, and then so you have the host name / whatever index it is. And I think just that part alone was almost half a meg of data, and then we have to send it to every MOM. So we replicate that 3,500 times, and so I'm not sure how many megabytes of data that was. But anyway, the system was overwhelmed, and it just said, "Oh, can't handle it. We'll throw it away," and the job can't start. Excuse me. Is there water back there?
On the podium.
Ah, great.
Ken?
Or
Yeah, underneath the podium.
underneath here. Great.
Ken, I could say there is something, UDP, I remember having customers in a prior job run into. A lot of routers have a feature called random early discard.
Right.
And it's applied to the UDP packets and
Yeah.
so on. And even if the router isn't fully loaded or busy, it will randomly throw away UDP packets.
Oh yeah, even if it's not busy,
Even
right?
if it's not busy, and which, you know, I was in telecom and voice over IP, which was horrible for your control messages.
Yeah.
And and it'll affect things like this.
Yeah.
Or you'll just never get something through.
So anyway, all the UDP related problems are now gone, and then for the most part, the communication is we open, send our message, we're closed, we're done. There are some exceptions. So Moab, for example, Moab comes up, it opens up the port to torque, and it leaves it open while it does all of its messaging. Queue Manager, until last week, did the same thing, but we took care of that. So it's not doing it anymore. And I'm sure there's some other utilities that are keeping ports open.
Just the German situation you cited, did we try it again?
Oh, so we got it fixed. We had to put in an option. We found that if we waited after every, all we had to do was just put a U sleep in. If we put a U sleep in after every message, it worked. I don't know why, but it did. So it slowed down the congestion enough on the network so that it would work. And so it's an option. I think it's even documented. I'm not sure. We may have gotten it done. If not, I'm sure there's a ticket on it that I haven't gotten to yet. So, but for most people, it doesn't really, you know, I guess I should go look it up. And somebody email me and I'll go look it up for you in case you have the same similar problem.
It would be also nice if we had, if there's any changes in the mom and kid calls that are related to this, options we need to add or delete, because we have to do some changes.
Yeah.
We're having some problems with Q stats, we were trying to do a lot of them.
Right.
And we just not.
Yeah, so this, now, so speaking of QStat, we'll get to that. Let me just go ahead and let's go on. Speaking of behavior, so I appreciate you bringing that up. Yeah, there might be some options that we need to go review the mom options, that's for sure. And one of the ones actually in Michael's presentation yesterday, with the Note Health Check, right now the mom's not multi-threaded, but we intend to multi-thread the mom. And actually it doesn't change the mom option, but we have to make sure that we take care of job start, job end. So we need to review all of those. Right now, yeah, as far as I know, we haven't reviewed all of them, but none of them have changed. So let's talk about behavior. So the server is multi-threaded. It's a lot faster, it's more reliable. You will not be waiting around for somebody else's QStat to finish. In fact, lots of people can be running QStat all at the same time. One of the quirks that we've discovered is on job arrays. So what happens when you submit a job array is we get the initial job array in, and then we schedule a task, or we spawn a thread that goes out and actually creates all the jobs, and then we return to you. And because we don't want you to have to wait, you've asked for 1,000 jobs to be created. Instead of making you wait until the 1,000 jobs are done, we say, okay, we've got it, and we start creating the jobs. Well, if you do that and then immediately do QStat, you'll say, my job didn't show up. And it's because it's not yet being done generated. Just wait a second, try again, and it'll be there. So there are things like that. So it's things that are being done in the background that don't show up. Like I say, this is the best example I can think of. The other thing is that if a thread gets hung up, so somebody else's thread hangs for whatever reason, everybody else can still continue to do work. They're the only ones that are out of luck. And and then they can modify it, but the server keeps on running. Like I say, the mom's currently single-threaded, but we do intend to multi-thread the mom. I don't have a time frame on that, but we want to get it done sooner than later. We have a lot to learn, so this is the part, we'll get your feedback as you guys start using this. Like I said, we have fewer packets dropped. We hope to, with things like mom hierarchy and job radix, take pressure off of switches. A lot of other things. Oh, another thing recently that we worked is the TCP timeout. The default value for that now is 5 minutes. And where you probably might see it is that, like with Moab, so I was having a problem and my TCP timeout was set to 6 seconds, and so every other iteration, scheduling iteration on Moab would be broken and say the resource manager was down. And that's because the server was only going to wait 6 seconds for something to come back on its socket before it closed. And so one iteration would go by and it worked, and then do the next iteration, try and use the same socket, and of course now the socket's closed. So that's just something to watch out for. Make sure that your TCP timeout is longer than your Moab scheduling iteration. So just some things that we've discovered. And that's it. So questions?